I recently got a question in an interview asking me to implement a time-based key value store. It's a really interesting problem, but I actually think it's something that we can put a spin on to make it even more interesting and more thoughtful around data structure and algorithm concepts. So the original question breaks down to the idea where we're asked to build a new structure called a time map, and this structure should have two methods attached to it. One should be set, which takes a key and a value, and then a timestamp that we put in and adds to the map, of course. And then the get, which actually goes in and takes a key and a timestamp, and then effectively returns a valid value based on that. Now, if you look at the base case inside of the LeetCode example, what they want you to do if there's multiple such values that meet less than or equal to that timestamp, it wants you to return the value associated with the largest timestamp available, but still hitting that condition of being less than or equal to. So I'm not going to spend a ton of time talking about the solution here because there's a bunch of videos and it's on LeetCode. So of course there's a million different solutions that you can look up, but suffice to say that typically what happens is you end up with a map implementation with O of 1 and then a get implementation with something around log of n, unless you're doing something tricky, where effectively with the timestamp search, you're doing a binary search because we assume that when setting records, they're put into order. So a visualization of kind of this implementation inside of, the LeetCode example is that typically you'll have the higher level map. You'll add something like dog. Dog will effectively be a pointer or referencing a array behind the scenes. That array will slowly put in noises for the value under dog. And if we go to search, again, you can imagine the binary search. So if we search for the timestamp of 2.5, right? The first higher than 2.5 value is howl. So the first lower than 2.5 value is wolf. So you can imagine if you've ever done binary search, how you could kind of slice that up and find that value easily. Now, one of the complexities with the setting, of course, is that when we add new keys, we need to do some kind of initialization work to ensure that, in the case of cat, if a brand new array needs to be established, it can be established, and then those values can be inserted into it. And then it's just business as usual, just like we see here in case 1. So you can dig a little bit more into this and check out the LeetCode problem. Again, that's 981 if you want to check it out. But we're going to spend our time together looking at an enhanced version of this problem and how you might solve it. All right, so in the enhanced version of this problem, we're going to be making a couple different changes. First off, when we implement set, it's no longer going to take a timestamp. This is simply going to be calculated at the time of the call. Then the time precision that we use when we make the implementation is going to be at a precision level of a nanosecond. Get is going to now start accepting timestamp optionally. Now, when get receives no timestamp, the implication is that we're going to return the latest key or I guess value for that key. So if in the case of this example, dog was called, howl should be the last thing that is effectively returned. And then if get does receive a timestamp, what we're going to do this time is we're going to do an exact match for that specific item. So if dog came in and we asked for 3, we should get howl coming back to us. All right. And then finally, we're going to implement a third function, which is actually just the same real logic from the previous example or exercise, which is to do a GetBefore. And GetBefore will take a string, it will take a timestamp, and it will effectively return all the elements that are before or equal to that timestamp. So things still get set in order, obviously, because insert is going to put the timestamp in when it does the insert. But this is effectively going to give us a list back rather than a single item. And some key things that we're going to consider here before we get into the design itself is that we're going to attempt to keep the complexity as low as possible. We're going to try to stay constant time for all of the get operations. The get before operation is still going to be something that is going to be log of n, but set and get are going to stay as close to constant as possible. All right, so let's talk a little bit about what the solution to this data structure might look like. So I'll just zoom in one here. So we know we still need to implement a time map at the highest level, and time map is something that's going to hold a bunch of keys. Now, what we're going to do this time is rather than having that key go right down to an array of values, we're going to implement a new type of structure called a time store. And time store is actually going to have 2 structures attached to it. So if you kind of follow it down to values, so time store and its reference to values, values is kind of like what we had in this original problem where there's going to be an array, or in Go's case, a slice of values, and we're going to have the ability to search through these should we need to, like in the case of GetBefore. Now, time index is going to be a map that holds pointers to those values. Now, what we're doing with this map is we're going to be able to facilitate that get command at a constant time, because what will happen is upon each insertion, we'll add a key to this map with that insertion timestamp and ensure that there's a pointer going down to the value in the array. And you'll notice here that these are kind of out of order, and that is potentially expected because maps don't have a guaranteed order. So whatever order they're in, we're just going to have a constant time lookup, and as long as we can resolve the appropriate timestamp, we're going to end up with the correct value. So with this structure in mind, time map pointing to a time store which holds a time index in a value array, let's look at how we might code this inside of Go. Starting off implementing the data structure, we'll first set up what a value is going to be. So this will be a type value, which is a struct. The first field is going to be the stamp, which is the time stamp. And then lastly will be value or string, which could be any object, but we're just going to hold a string value in there for now. Additionally, we have the time store struct. As a reminder, time store is going to be the holder of both an array of those values along with this time index construct. So inside of time store, we'll start with the time index. Now, the interesting thing about time index is that the key is actually going to be a structured type. It's going to be from the standard library time.time. And then the value is going to be a pointer to one of these underlying values. All right, now the actual values themselves are a slice of values, and then we can end this here with the time store struct. Now we have the higher level time map struct, and this is going to just be a map of strings. This will be keys like dog and cat, and this will hold a pointer to each instance of that time store. And this is largely our data structure that we need to set up. So a key thing to keep in mind is that this time store construct that is kind of the holder of both the value array and the overlaying index is going to have a unique time store for every type of key, so dog, cat, and so on. Next, we're going to implement a constructor and two convenience functions. So starting off with the constructor, it'll be a pretty standard constructor in Go. This is going to be a new function that returns a time map. The actual return is quite simple, so we're just going to directly return a new instance of a time map. And for the key, we're going to set times equal to an initialized map where the key is a string, and the value is a pointer to a time store. So again, this will be cat, pointing to the time store for cat. We'll end that, and now we have our constructor for time map. Now, a couple more conveniences that we want to put in place. We want to also have an internal constructor for the time store itself. We'll, of course, call this when a new key comes in, and we need to initialize a new time store for that key. So similar to the new for time map, this will just return the time store. It's going to have the time index initialized, which is that map of times where it points to the value, and the underlying value array as well that we are going to be able to search through when we need to find things that based on timestamps come before something. We'll end that, and now we've got our constructor for the new time store. And then last but not least, we've got the actual get time store function. Now this will be quite critical in our get calls because we need to see if a key exists and that there's associated time store. If there is, we want to return that time store so we can actually do lookups. Otherwise, we'll return an error. So what we'll do with Go is we'll start with the notation where we check to see if the key exists. And if it does exist, we'll store it in the TS variable. Then if we've got that, it's a good case. We just need to return the time store in a nil variable to the caller. We'll close that out. And then at the very end here, if we don't pass that, we know that the key did not exist. So we're going to return a nil value for the time store and then an error letting the caller know that that key did not exist. We'll close that out. And these are our constructors and helper functions for this data structure. With the constructors and helpers created, we're now ready to do get, set, and get range. Now, from a time complexity standpoint, again, we want to focus on all cases of get being O of constant time, set the same, and then get range, we're still going to accept the log n from the binary search. So let's start off with actually setting values inside of the map. To start this off, we're going to declare the set signature. This is going to be attached to the time map object, and it is going to accept a key that also will accept data, and both of these will effectively be a string. Then we're going to check if that time store exists. This is the key thing. If the actual key is in there and if there's a time store associated with it, we're ready to just insert into that existing value array. So if that is the case, we're ready to insert. We'll establish a new time by getting the current time. We'll then go and establish the value, where the first field stamp is that timestamp we just captured. The value is the data passed in as an argument. And then we're going to look at the time store values, which is that array or slice of values. And we're going to append that to the existing time store values with that new value we just created. So now the list is filled up. But remember, if we look back at our diagram, as we're adding things into the list, we also need to be sure that we're maintaining this time index, which has the map pointing into that element in the list. So if we go back here, we can now access the time index by saying timestore.timeindex at stamp. This is going to be equal to that value, and just keep in mind that this value is a pointer, it is not a copy. So we're going to ensure that they're looking at the same memory address. And then if all goes well, we're just going to return, which might feel a little obscure right now, but I'll show you why this is helpful. We'll close out the if, and this effectively becomes our base case for this algorithm. Now, if we get out of the if, that means that the key did not exist, in which case we're best off going ahead and doing a new time store right here. And this new time store will set that to the key. Now, what's interesting here is we're then just going to recursively call set, because now that we've got the time store associated with that key, we're actually ready to just hit this base case and do the actual insertion. So we'll do the recursive call and end the function. And this is all of the logic we need to do for set. Jumping back to main, this would be a good time to test and ensure that set is working as expected. So what we're expecting here is that as we add keys in, we get a new time store. We want to make sure that values are filled up and that the time index is pointing to the appropriate underlying value. Inside of main, what we'll do here is start off by creating a map of keys with values that are effectively array. And in this case, we have dog, we have cat. You can see the different sounds that these make, and this will be our sample data KVS. Now, building off of KVS, we're going to create that new instance using our constructor of time map. We'll refer to this as TM going forward. And then what we want to do here is we want to loop through KVS. So effectively, for each animal, and for each animal key and for each sound array, we'll go ahead and bring these through. And then we want to loop again. And in this case, we don't care about the index inside of here. We just care about the specific sound, and we'll range through the sounds. So what we'll do is we will do a set inside of our map for each animal and each one of its sounds. And then we will close this out. And now we've got theoretically a time map that is all set up and good to go. Now, a tool I like to use when I'm setting up algorithms, especially with data structures like this, is I like to use Spew, and you can find Spew at this GitHub address just with a quick go get. You can get it in any of your projects. But with Spew, I use it because it prints out and kind of traverses a data structure. It'll even follow pointers, dereference them, and really help me understand what I've built and whether it's working as I expect. So with all of this said, I'm going to save the file. We're going to go over to a new terminal window, and let's do a go run of main.go and see what we get back. Now, we're getting a lot of different output here, and what we'll go ahead and do to examine this output is maybe just put it through NeoVim for a moment, and I'll say set no wrap. There we go. That'll make it a little bit easier for us to read. Now, it's not stylized or colored, so a little hard to read, but bear with me here. We know that the times map exists, and we can see that it has a length of 2, so dogs and cats. Inside of time index, we effectively have all of the different cat sounds right here, and then the values for those cat sounds. So this is the value array. As a reminder, that's here, and then the actual map. Now, one thing that's probably worth checking is to make sure that the values are pointing to the same memory address as the map. So let's take a quick look at Screech as our example. So Screech is at the timestamp of 60431, and you'll notice here, if we go to kind of the end of Screech, that its memory address at the very far right is the 0x ending in 8510. 10. So that's 8, 5, 10 for Screech. Now let's go back down to the values array and find Screech again, and we'll see that timestamp at 60431, and we'll see the address is 8, 5, 10. So effectively, while they are being referenced in two different data structures, we do know that it is the same underlying value in memory that is being pointed to and will be accessed regardless of how we get to it. Speaking of getting to it, now let's talk about implementing the get functionality. As a reminder on get, we want get to be able to receive no timestamp and return the latest value for that key, or to receive a timestamp and send the single element back that matches that exact value. So to set up our signature here, we know that we're going to have this attached to the time map. It's going to be called get. We're going to accept the key string, and we're going to use variadic functions here. That's what the 3 dots are, to accept technically a list of times. Now, why I'm using this is in that list, it actually can be 0 or no elements all the way to multiple elements. Now, we'd want to think a little bit about our API signature and documentation for instructing users on how to use this, but this is actually inherently going to make things work in an optional manner for stamp. Now, once stamp finds a value, assuming it does, it will return a pointer to that and an error. The last thing I'll say on this value pointer is it does enable the people getting the value to potentially mutate it. We're not going to worry about that concern for this exercise, but potentially sending back a copy could be better depending on what you're trying to do. So first thing we're going to do is try to get the time store for that key or get an error out. And if it is an error, we'll just return the error back and end execution of this function right here. Now let's assume we did get a time store back, or in other words, the key does exist. With that being the case, we now need to figure out, did the user provide a timestamp? Now, if the user did not, or in other words, because again, stamp is going to come in as an argument that will be featured as an array. So if it's less than 1 or the user did not specify that, what we want to do to achieve O of 1 is actually go in through the values array and release the, or not release, but return the last element inside of it, because as long as it's sequential, which is part of the constraints, it is going to always be the latest. So what we'll do is we will return the time series values, or sorry, the time stores values at the very last element and return nil for an error. So this is a very simple case when no stamp is put in place. But what if a stamp is put in place? Well, if a stamp is put in place, we know we actually want to access through the time index because we want that constant time of looking up the timestamp and then grabbing a value out. So again, we're going to just grab the first stamp value in the array. This is again a bit tricky for API callers because they technically could put in multiple stamps and we need to think about how to handle it. But in this case, assuming a list of stamps or some amount of stamps were provided as arguments, we're just going to grab the first one. Then we're going to grab the time index and try to look up that timestamp and see if it exists in the key. So this is both capturing that value and also seeing if it did find a key. Well, then if we find a key, simply return that value in a nil error. Now, if we did get this far and did not find the key, that's a problem because we had the key inside of here, but we did not find a correlated timestamp. So we're once again going to return nil for the value, and we're going to provide an error back to the caller. So effectively, this is our get logic for both getting when a timestamp is provided and when it is not provided. Okay, so now we're back inside of main and we can test out get. First, we'll capture sound for the latest value that was added to dog. This should be the latest because there is no timestamp inserted. If an error is returned, we will panic. Then we'll just print out sound and see if that works. In the case of dog, the last sound inserted was whimper, so we should get that returned. Next up, we will iterate through our map of times and grab the map for dog under time index and actually just capture all the timestamps we know about. So we're kind of doing some trickery here since we have access to the underlying data structures. We're just going to capture them all. So in each case, we will do dog for each stamp and we will capture the noise. If it's error, which it shouldn't be, we will panic, but we'll go ahead and print out this kind of pretty printed way of saying for this stamp, I correlated to this noise, and that will just guarantee us that our lookup is working for the get operation. So now we've got this in place under for, and we should be good to test this out. Back in the terminal, let's try running this. So we'll do go main, And we have imported but not used spew, so we'll fix that real quick because I did get rid of the spew command to make the output a little bit cleaner for this example. All right, and now we can see the first print that has no metadata around it, which is whimper. That's exactly what we would expect here. And then we can see the insertions and the timestamps for each value. Now, I don't exactly know without doing the dump what the correlated insertions were, but here's one way that we could kind of validate it. So if we go back to our sample data, let's take a look at wolf and bark. We know that they should be the two newest items. We're actually better off. Let's do wolf and whimper. So this should be the newest, this should be the latest. So for wolf, if we look that up, we can see that the timestamp is clocked at 91553398. And if I look up at the 3-digit here, it looks like this is in fact the first one inside of that timestamp. So this is the right time for wolf for sure. And then if we look at whimper, we can see that it's 971555357. And if we start at the 5-digit, we know there's a couple 5 digits. But then if we look at the 3-digit here, you can see that the 3-digit does not have anything higher than it. There's a 47 here, there's a 52, there's a 50, but 53 is the latest in nanoseconds. And whimper is in fact the last element inside of here. So overall, I would say get seems to be working as we would expect. Last up is our implementation of GetBefore. It's the most complicated, but still not that bad. GetBefore is going to accept a key, it's going to accept a timestamp, and it's going to return any elements in the list that are less than or equal to the timestamp that's passed in. So let's visualize this with our graphic for a moment. Pretend wolf is at timestamp 0, bark is at timestamp 1, and howl is at timestamp 2. Now I know these are indexes, but just pretend they're timestamps for a moment. Let's pretend that you inserted a timestamp search at 1.5. So clearly 1.5 is less than bark, or sorry, it's greater than bark and less than howl. So what we basically want to do here is we want to identify that first greater than element, which will be howl. And if we can find the index of howl, we'll then know, since these are sequential, that everything that comes before howl should be returned as part of GetBefore. Jumping back to our implementation, let's look at what this might look like in Go. So we're going to attach GetBefore to the time map, nothing new here. It will accept a key and it will require a timestamp this time. So that will be part of the arguments. The return is going to be a list or a slice of pointers to values. Same consideration, might not be that smart to be sending pointers to value back, but we'll just keep it as is for now. And then a error if something goes wrong. So first thing we need to do, does the key even exist? If it does not exist, we will just return the error to the caller in a nil set of values. Now, if it does exist, we now need to do the lookup and search. So what we're going to focus on here is using sort.search. Sort.search is going to accept the length or size of the slice that we want to search through. So this will just be TS values. And then it will allow us to implement a condition for which it will be true. Now, what do I mean by condition for which it will be true? Well, let's look at search inside of the standard library for a moment. What's interesting about search is it's going to do a binary search. And what it does is it's actually going to return the smallest index it finds that matches the condition we specify. So this correlates directly to this example where in the case of inserting 1.5 here, we know that if we insert 1.5, howl at 2 is going to be the first or lowest indexed element that matches that condition. Let's pretend for a moment again, 0, 1, and 2. Let's pretend for a moment that you insert 0.5, okay? Technically bark at 1 and howl at 2 are greater than 0.5, but search will return the smallest index. So it would return bark as part of 0.5, and then everything to the left of that, if we knew bark's index, could be returned as part of the result. That is basically what we want here. So we will head back in our code to where we were implementing search, and what I'm basically doing here is I'm putting the condition in for this function. So let's take just a quick look at what's happening here. So as an argument, function iInt, I is going to be the currently evaluated index. So we just look in our array and pass in I, and then we can look inside of I for the stamp. And since this is a time.time object, there is the after method that we can call and provide it the argument. So we're comparing stamp in the currently evaluated data structure element with the stamp that was passed in as an argument to GetBefore, And once again, if we can identify the index because there's a match of the lowest index that is after, we will get the index and be able to return all the things before. So let's assume for a moment that we do find that. And the return call just looks something like this, which is a little bit clever, but still understandable. So the idea here is that if we look at the TS values, it's going to return from the start of the array all the way to the index. And now this index value is non-inclusive. So let's pretend for a moment we have index 0, 1, and 2. Let's pretend for a moment that it returns index 2. Okay, so for how, meaning that we're at that 1.5 condition, we want to release or return these two. So in this case, we now know that the index is going to, or the expression is going to evaluate to 0 and then go all the way to 2. Now, since 2 is not inclusive, this actually means that what's going to be returned is 0 and 1. If everything in the array, for example, was before, this kind of always tricks me with Go, is it's actually going to evaluate like this. And you would think, oh my gosh, an index out of bounds, right? But again, it's not inclusive. So you're actually going to get 0, 1, and 2 returned in this result set. And then of course, if it finds that the first element in the array, let's pretend wolf, is actually after the timestamp that's provided, nothing should be returned in that case. So this is going to evaluate as 0, 0, and then your result set is effectively empty. All right, so we'll back up here and go ahead and put this together, and I'll highlight it here. This is the end state. I guess it's a little too much to highlight. This is the end state of our GetBefore function, and it is going to do exactly what we'd want. So let's test that out as a final step. All right, back inside of the main function, let's do one final test for GetBefore. So GetBefore is a little tricky to test too. We'll start off by getting a slice of times, and we'll collect those slices by looking inside of the dog key for its list of values. If we iterate through every item inside of dog, we can capture the collected stamps and add them inside of here that we can then use for searching. You might notice that I actually had to access values and not time index because time index doesn't have a guaranteed order. It's a map. So by going through the values, I actually know that the indexes I'm collecting for collected stamps correlate in order to the timestamp. So it will once again be chronological. Okay. Now inside of here, I'm going to instantiate something called before time, and this is going to use time.parse, where this is actually just a parsing argument for formatting, and I'm giving it the argument of 2007. So this will evaluate to January 1st, 2007, which should be way before any of these map insertions happened, which should give me an empty slice back. We will then just print that out to be super clear. And then we're going to capture in the variable all before using the GetBefore method we just implemented, dog and the before time argument. So again, this should be totally empty when it returns. All right. And then if that error is nil, we'll just go ahead and panic and we will dump out the full result set right here. Okay. So we're going to jump back to the terminal and run this in main. And we can see here some of our old output, but namely you'll notice that when searching for 2007 January 1st, we get a completely empty result set of values back. Now that's great, but let's make sure we can get values back with a more appropriate date. And that's why we collected these collected stamps right here. So what we'll do is we'll uncomment out this index to try, and we will get rid of the before time. And I am going to pass in as an argument collected stamps with index to try right here. So collected stamps, index to try. All right, and now we should be asking for the thing at timestamp 2, or the collected stamp 2. Now, if we go back up to dogs, 0, 1, 2 is psi. So we're going to insert the timestamp associated with psi. When the search happens, if all goes well, this should realize that growl is the lowest index after that timestamp, and we should effectively get wolf, bark, and psi all returned to our client call. Heading back to our terminal, we will run this again, and now we can see that we are searching before. So we'll look at, this is 53.8.508, right? So 53.8.508. So we do know that we searched for psi right here. So that's good. So 53.508, 53.508. And then inside of here, we got wolf, bark, and psi, omitting our whimper and omitting our growl, which came after that inside of the sample data that we put in. So GetBefore is also working exactly as we expect. So wrapping this all up, I hope you found this to be kind of an interesting problem. I think that it's kind of a cool way to think about how like data structures can lay on top of data structures and achieve certain time complexities. And there are definitely some trade-offs that we should talk about. For example, the memory of this data structure will grow quite a bit more than just having an underlying array, because we are maintaining this time index of map keys as it grows. And if we ever do deletions, or we're already doing insertions, but perhaps deletions, it is a bit more complex, especially if we ever have to concern ourselves with thread safety, which is another piece worth mentioning. This data structure is certainly not thread safe. We would need to think about what our thread safe thread or multi-threading needs are, and then maybe consider things like mutexes or locks to actually make that happen. All right. So the last thing that I will kind of just point out, although this is kind of a deep optimization consideration, is that since we effectively have like pointers pointing to pointers pointing to pointers, it's going to be a lot less likely that this ends up, or this data structure ends up in the CPU cache. CPU cache is a very, very fast way to access memory. And typically things that land in CPU cache are oftentimes contiguous memory, things like arrays, and the access speed of those can be super, super, super fast. But again, in this example, we weren't focused on that level of optimization. We were really focused on what could we do to get constant time complexity of accessing these values in these different contexts really quickly. So again, hope you found this really interesting. I personally find these types of technical interviews to be extremely hard. I will admit, even though I've been programming for years, I feel like I am programming for my first time ever when I'm kind of put in the hot seat and asked these kind of questions. But independent of not really loving the style of these live interviews, I do really find the thought process around them and the exercise itself really intriguing, and I hope you did too. So that's all for now, and I'll see you next time.